Okay. All right, let's get started. Okay, so today I'm going to talk about the design of the Deephaven Learn library. We'll have a follow-up call where JJ will talk about how to actually use the Deephaven Learn library. So first question, what is this? And Deephaven Learn library is how you combine Deephaven and AI. So AI universe has a lot of different technologies. You have TensorFlow, PyTorch, scikit-learn, and probably 100 other things. We needed a way to make all of these technologies work and work efficiently. So under the covers in these libraries is a lot of math. You end up with neural networks and related things that do a lot of add, subtract, multiply, and divide. And you end up with scenarios like this plot here where the x-axis is the number of gigaflops and the y-axis is the accuracy. And the more computing you throw at these problems, the more accurate they get. That is an interesting computing problem in itself. And that's where GPUs come to the rescue. So if you look at a CPU, it has a handful of cores on it. If you look at a GPU, that typically has a few thousand cores on it. So if you're doing a lot of the same mathematics, GPU is going to give you substantially better performance. But to make this work, you have to feed the GPU sufficiently. So if you only do a small number of calculations, only a small number of these processing cores will be active for each step. If you look at the performance of a GPU versus CPU, the x-axis here is the data size, the y-axis is the execution time. You can see that the GPU performance is pretty flat. So you would like to send as much data to the GPU to work on as it can handle at a time. Then we have Deephaven. And with Deephaven, we have to look at how it processes real-time data and how queries are structured. So the first thing we'll look at are the queries. So a Deephaven query is structured as a directed acyclic graph. So if we look at this image on the right, let's say you call the timetable function to create a table. That makes a table. Then let's say we use update to add a new column named label. Well, that will create a new table, which we'll call T1 here. Then let's say you use last by to get the last value, to get the row with the last label column. That will create a new table T2. Then if you want, you can join tables T1 and T2 to create table T3. And this is the directed acyclic graph, which the query represents. And if you look at real-time data, as these root nodes change, those changes end up going through this graph and updating the tables, which leads us to the update graph processor. So if you have a table, that table, when it changes, produces a record of what changed. So it will tell you what rows were added, what rows were modified, what rows were deleted, and what rows were just shifted around. And that message then goes to the next table for it to update its state, which then results in changes that it sends down the line. And the update graph processor manages the calculation of these updates and propagating them through the directed acyclic graph. So the question we have is, how do you marry a GPU and an update graph processor together? And that's really what Deephaven Learn is doing. So let's step back and think about how we might want this to work. So if we start with a table, then we have an update message. With that update message, we can convert into a NumPy object. So we can look at the data from the added rows and the modified rows, and that can be used to create a NumPy array. Then those arrays could flow into a library like TensorFlow, which itself could be using GPUs or TPUs or other hardware. Then TensorFlow itself may output its own NumPy arrays containing results. We could then feed those NumPy arrays. We could use those NumPy arrays to create change events, and then that could update a new table. And so this is kind of how to think about Deephaven Learn. At this point, the key design decision was to generalize. We want to avoid context and specifics. We want to generalize and keep repeating the generalization. So like these trees, they're all trees, but you can represent them as something more simple. And this ends up being useful here. So this progression we're going to break into 3 parts. We'll call this first part the gather part, where you take a change event and then output a NumPy array or something. And then we'll have a middle phase, which is a compute phase, which takes inputs, it performs some type of AI calculation or other logic, and creates outputs, which may be NumPy arrays. And then we have finally a scatter operation, which takes these outputs and then puts them into an output table. So first, let's take a look at gather. So in gather, your AI logic may want data in various different forms. It may want a NumPy array, it may want an image, it may want a tensor, it may want a sound file. And we have to get there from a table. So in the middle here, how do we want to represent this? And what we've done is we've created an input object where you provided the columns of the input plus a function to create the output. So for example, if you may take columns A and B and use that to create a tensor, which is used later. And this is how this step is abstracted. Then if we look at compute may take in any number of different types of data. It will perform some logic, could be TensorFlow, scikit-learn, PyTorch, whatever your favorite logic is, and then it may output results in all of these values, or they may be scalars. So here we can just abstract this by saying the compute is just a function. We really don't care what library you're using or what hardware you're doing it on. Okay, and then scatter. We have kind of the opposite problem from the inputs, where we have data in various formats. We need to take that and put that into columns in a table. And to do that, you have an output object. And here, C is the output column name. You have a function to go from the outputs of the AI model to the values in the table. And then you have an optional value you can add, which is the type you would like to cast the result to in the table. So this would be the type of column C in the output table. And so if we put this all together, you end up with this syntax. So you have the learn library and the learn function. You have the source table, which is the input table to all these calculations. And you have the result table, which is the output table from this. Then model func right here is the function you use to define the logic that is being computed. And here you have your inputs, where your input columns and your function to gather those values into objects is, and then you have your output, which is the inverse, which is the column it's going to, a function to get the values, and then the type of the output column. The one thing I haven't talked about here is this batch size. And what batch size is it is a limit on how many rows of data will be processed at a time. So if you, for example, if you have a GPU, that GPU has a finite amount of onboard memory. And so you may decide that that GPU can handle 1,000 rows at a time in memory. And so you can use this value to cap the value there. For example, if you use 2,000 rows, that may overrun the memory you have available. And that's what that option is for. So, to summarize, Deephaven Learn is Deephaven plus AI. The way it was designed, it will work both on real-time data and static data without changing your code. All you have to change is the input table. You can make this work with any AI library. All you have to do is change the functions to create inputs, scatter outputs, and perform the logic. And this can work with any hardware that your AI library can work with. You can run this CPUs, GPUs, TPUs, it doesn't matter. And with that, I'm happy to take any questions.
So at the start, you mentioned something about the table update and how that's kind of shared across all the tables. Is that the same update that goes into the listener functions?
Yes. So when a table changes, it has so a table can have listeners on it, and those listeners listen for the change events that have add, modify, delete, and shifts. So yes, that is the same thing as the listeners listen to.
Cool.
Right. Anyone else?
Yeah, so I use Deephaven Learn pretty often, and I'm particularly interested in getting access to GPU, TPU, external resources to make my queries faster, but I am not too familiar with how to get access to those resources inside of a Docker container. Is that something that you have experience with, or something that we could?
Yeah, so I've done that before. Typically, I've done it with NVIDIA, but there is an NVIDIA Docker image that has this already set up. And on your host machine, you have to have the NVIDIA stack installed. And then I think there are a couple of options. You pass to Docker, and then you use a container with the necessary drivers installed, and then it can work. For things like the cloud providers, I think they provide instructions on doing this, because you can just grab VMs with this hardware installed. Right. Anything else? All right, awesome. Thanks, everyone.